Okay, Assalamu alaikum guys. Today we will continue on the tutorial of Rankine cycle because last time we did a tutorial for or a review for solving the quizzes. So yeah, we will continue today with the Rankine cycle. I don't know why none of you answered on the chat. I suggested that we have a review session before the midterm. I don't know if none of you are interested or what, but I'll do a poll. Okay, I'll send you an email and do a poll. And yeah, if you are interested, you can vote for a day, for a suitable day. And yes, okay, for doing the review session. Today, I want to show you an interesting tool, okay, that will help you in doing next homework, okay, which is the homework for Rankine cycle, and also when you are studying. This is MATLAB code, okay, that will give you the Steam values or Steam tables to have it embedded in there. So instead of always doing interpolation, it might be very tedious to do it, of course, for maybe when you are solving a lot of problems, you solve 20 problems, something like that. You don't want each time to interpolate and get the values from the table, okay? You just want to practice on solving problems. So this is the code, okay? You can download it from here, okay? X steam, thermodynamic properties of water and steam. I'll put the link there for you in the chat. Okay, so we'll use it today in solving our two problems, okay? And it have a manual there, okay? This is its manual, which will show you how to get each function. The pressure is a function of what, and this is a function of what, okay? But remember, this is code is only for steam, okay? For air properties, you need to use the normal tables. So yes, let's start, okay? Our first question is a question that is similar to the, or I guess it's the same as the homework problem, okay? But there's I think it's with different numbers, okay? So let's start. We consider that we have a coal-fired steam power plant that produces 175 milliwatts or megawatts, sorry, of electrical power. The power plant operates on a simple ideal Rankine cycle. So it's an ideal Rankine cycle, meaning that the isentropic efficiency of the compressor equals to the isentropic efficiency of the turbine equal to 100%. Okay, keep that in mind. And what else we have? We have the operating conditions for the turbine. So the turbine enters or the inlet of the turbine, okay, is at, which are properties at 3. So I'll write here state 3, okay. We have temperature equal to 550 Celsius, and we have a pressure of 7 megapascals. And at state 4, okay, we have a pressure of 15 megapascals, 15 kilopascals. And what will be the temperature? We don't need the temperature actually here in state 4, because remember, this is state 3, that's the point. Now the turbine have 100% efficiency, so it will go straight down with constant entropy. Okay, this is the TS diagram with constant entropy till point 4. So from point 3 to point 4, we have constant entropy. So from those two states, we will get the entropy. And of course, we will get the H because it will help us in calculating the efficiency as the question will ask you. And yeah, and so you make the S constant. So S3 will be equal to S4 and you will get the H here, okay? And what else we have? Yeah, we don't have the starting point at point 1. We only have, he tells me that, okay, this is, I don't know if this will be inside the dome or no, okay? You can see that later. But what he tells me that this is the condenser pressure, which is 15 kilopascals. And I know that the boiler pressure is 7 kilopascals, okay, or 7 megapascals, as he's told me that state 3 have that pressure. And we know that the pressure from 3 to 2 is constant, and the pressure from 4 to 1 is constant. But where is point 1 located? It might be subcooled somewhere here, okay, or I guess here, okay, because this is the line of constant pressure somewhere here, or it might be here, okay, starting from the saturated liquid. If the problem does not state for you, remember that always, if the problem does not state for you where is the starting point of the cycle, point 1, and there are no enough information to know it, like you don't know point 2, where is it located? So you go down to 0.1 with constant entropy. So you just put it here in the saturated liquid. So this is an assumption that we will make. 0.1, okay, which is the inlet to the compressor, is saturated liquid, okay? Remember this assumption. It might not be given for you always, so remember it. So this point is a saturated liquid, and now we can go straight, okay, till we meet the pressure of 7 megapascals, then we stop, okay, with constant entropy. Okay, so and state 1, we know that state 1, okay, is saturated liquid at which pressure? At pressure of 15 kilopascals. Remember, the pressure from 0.4 to 1 is constant. And state 2, okay, we have the pressure equal to 7 megapascals, and we have the entropy is equal to entropy of 0.1, okay? And the entropy is equal to entropy of 0.1. So yeah, let's start solving the problem. What he wants from us, he wants the overall plant efficiency, which is the ratio of the net electric power produced, okay, output to the energy input as a fuel, okay? What is it? This is actually after you find the efficiency. He gives you an efficiency for the. Sorry, I didn't read the problem, all of it for you. Okay, the coal has a heating value. Okay, this is the heating value of the coal. Remember it from thermodynamics. Okay, the heating value, meaning that for each okay, for burning 1 kilogram of coal, what amount of energy you will get. Okay, so when you burn the coal, which is gonna be simply the heating source, okay? The heating source that will provide the heat addition for the cycle. So this is the heating value of it. And he tells me that 85% of this energy is transferred to the steam. So this is the combustion efficiency, okay? Meaning that whatever is being combusted here as a fuel will not be all of it transferred to the cycle. Only 85% of it will be transferred to the cycle. And then again, he gives me another efficiency, which he tells me that this is the efficiency of the electric generator, meaning that whatever network here produced, okay, network that is produced there, some of the amount of the work will be gone to the compressor, of course, and whatever network is produced here will be utilized in a generator, yeah, an electrical generator to produce electricity. And then the amount of energy, okay, that will, or the power that will this generator give me, okay, the electric power, also will not be 100% of the net power produced here. So it'll be 96% of it, okay, as he tells me. So what is the overall plant efficiency? Okay, remember also in thermodynamics that I have 3 systems now. I have the fuel, I have the electric generator, and I have the cycle, okay, the cycle. So if I want to find the overall efficiency, what should I do? The overall efficiency is the ratio of the okay, output to the first input, okay? This is the first input, okay, the input from the fuel. And that's the furthest output, which is the output from the generator. I don't care what happens inside the cycle, okay? This is how we used to deal with systems, okay? Systems that are connected, okay? So you just take what is the first in and what is the last out, okay? And then you put the ratio of them, okay? Which is the ratio of here, what is work out or power out, and here what is power in, okay, or heat in, okay? And then I put them as a ratio, okay? And this is the overall efficiency, the plant efficiency. But unfortunately, or not unfortunately, we can do this in a simpler way, okay? Because I can calculate the cycle efficiency because I know how to deal with the cycle and I know what's the efficiency of the cycle, okay? Instead of computing the work here and computing the energy input here. And then what I should do, after I find the thermal efficiency of the cycle, I have that equation that will tell me that the combined efficiency is equal to the efficiency of each individual system. So I multiply the efficiency of the cycle with the efficiency of the combustion, okay? This is combined, this is combustion, and then multiply by the efficiency of the generator, okay? So the 3 efficiencies of the systems are multiplied with each other, then I will get the combined efficiency, okay? This will be easier than see what's ratio, okay? I can know what's the heat addition to the cycle, and then from that I will go up, okay? Because I have 85% of that is transferred, okay, from the fuel to the cycle. So I should divide, okay, to get what's the power in from the fuel in the beginning, okay, or what's the heat was that was combusted and okay, that I got from the fuel. Okay, so I will calculate what is the heat addition here, and then divide it by 85% to get the amount of heat that was produced from the fuel. And then here, after I get the power output or the net power output from the cycle, I should multiply by 0.96 to get the power produced here from the generator, and then divide those ratios together. This will be a lot of work. Why don't we calculate the thermal efficiency of the cycle and then multiply by those two efficiencies, okay? So yeah, the rest of it, let's just get the H's and the question will be done, okay? So I'll use the MATLAB code for that, okay, to make everything easier. What is the thermal efficiency of the cycle? The thermal efficiency of the cycle is either the amount of work, okay, work net, okay, over Qn, which is equal to the work of the turbine minus the work of the compressor over the Qn, or it is equal also to 1 minus Qn over Q out. Okay, so for this one, I need H3, which I have all the properties for, minus H4, okay, which I can then find. It will be the same as H4S and H4A are the same because I have 100% efficiency, okay, isentropic efficiency, and for the compressor, it will be H2 minus H1. And again, it's the same thing. I don't have actual and isentropic because the isentropic efficiency is 100%. And this one will be the heat addition, which is H3 minus H2. Okay, so I basically need all the points. Or even if I worked here, then for the heat addition, I need H3 minus H2. And for the heat out, I need H4 minus H1. Okay, so either ways or both ways, I need all the points. Let's use this one. This one is easier. Okay, so what is H3? What is H2? What is H4? What is H1? Now H3, I have the temperature and I have the pressure. So go now to the MATLAB code, okay? I've already run it here, okay? So you know how to open MATLAB, okay? Then after you open MATLAB, then you put that you want to open a file, okay? And then search for that file where you download it, and then the code will be run, okay? This is the code. Okay, this is the code page, okay, XST, this is its name. So yeah, and then here you go to the command window where you work with the values. Okay, so when you start, you should write xsteam. Okay, this is what you write at first, xsteam, and then you open two brackets, and inside those two brackets, the first thing is what properties I want to find and what properties do I have. Okay, so what I have the pressure, okay, and the temperature. Okay, it should be pressure first, then temperature. Okay, that's how the code is defined. Okay, you can look at here in the manual of the code as I told you. So I want H from the pressure and the temperature. Okay, this is how it is written here. Okay, so I want H from the pressure and the temperature, and then comma. Okay, after those two things should be put in between what we call them. Okay, let's call them are these parentheses? I don't know. Okay, but should be okay. Quotes put in between quotes, and then we need to put the pressure, which is the pressure should be in bar. Okay, the pressure in this code should be in bar. So I have 15 what megapascals do we have? 7. Let's remember. Yeah, I have 7 megapascals, so they will be 70. Okay, in bars, and the temperature is 550. So now enter, and then here you go. This is your H3. Okay, as simple as that, without going to do interpolation or anything. So H3, I know it. It is 3531.53. 3531.53. Of course, kilojoules per kilogram. Always write the units, okay? Don't forget to write the units. So what is H4? How can I get H4? Simply, H4, what we have only the pressure, yeah, which is the condenser pressure. But I told you that we can use the entropy, okay, the entropy of point 3, okay, because the entropy is constant from 0.3 to 0.4. The entropy is constant. So I will use the entropy of 0.3. I need to find it. Again, you are going to make another interpolation in the table. Why is that? Just as simple. S, okay, and from the same properties, now I just want S, okay, I want S3 to know it and then put it as S4. So this is S3, okay, now it's saved as an answer. And now, okay, I want H, which is H4, from knowing the pressure and the entropy, okay? And what is the pressure of 0.4? It was 15 kilopascals, yeah? Which is a transfer to 0.15 bars, okay? Always write it in bars. And what's the entropy? The entropy is the previous answer that we find, okay? ANS, which is the entropy of 0.4, of 0.3. Now, this is the H of 0.4, 2252.65, okay? So H4 is 2252.65 kilojoules per kilograms, okay? See how simple is that? And then let me enlarge this and delete some of these here. And now, what points also I need? I need H1 now, okay? H1, we said that it is saturated liquid, okay, and we know the pressure for it. And H2, okay, which is after the compression, okay? So let me go to the code, okay? Now for H1, I know its pressure, okay? And that's the only thing that I know. But what I want to get H, okay, for the saturated liquid. It's called HL in the code, okay? Again, you're gonna find it here in the code manual, okay? If I have the saturation pressure, okay, what should I do here? It tells you, put for me HL, which is saturated liquid enthalpy at that pressure, okay? So what's the pressure? The pressure is the same. I don't need two inputs. This function only have one input. Press enter. This is your H1. It is 225.94. Okay, so 225.94 kilojoules per kilograms. And you remember how we used to get H2, okay, here, especially here in this course, because you don't have table A, what we call it, A6, okay, or not A6, A7, the one for the compressed liquid. You don't have that table. So what you do, you get V at 1, and then you know the pressure at 2, and you know the pressure at 1, and that's how you get the compressor, okay, the pump. Why I'm saying compressor, the pump work, okay. In liquids we use pumps, and in gases we use compressors. So the pump work, V1 P2 minus P1, and that's how we get it basically, okay. But here no need to do that, okay. You have the code, everything is there ready for you. Get S1, okay, and then equate it with S2, and then you use S2 and pressure 2 to get the properties, okay. That's instead of using table A7, okay, and that's gonna give you the most accurate answer. This one is an approximation. So again, what is S of 0.1? I want the saturated liquid entropy. That's it. And then from knowing the pressure and the entropy, what was the pressure for 0.2? It is the same as the pressure of 0.3, which is 70. And then put the comma, and then answer, which is the same entropy as 0.1. Okay, and then delete this. Okay, I want the H. Hit the enter, and then I have it 232.99, which is 233. Okay, so it is 233. 233 kilojoules per kilograms. Okay, now I know all the points. And now my thermal efficiency, or my combined thermal efficiency, is gonna be, oh, let me delete all these. My combined thermal efficiency, okay, combined, is gonna be the efficiency of the combustion, which was 0.86, minus the thermal efficiency of the cycle, which is 1 minus. Now open this. I want in the top, which is the heat out, which is H4 minus H1. Okay, it is 2252 point what? 0.65. Subtract 225.94, which is H1. So this is 1. This is 4. Okay. over now H3 minus H2. H3 is a 3, 5, what? 353, 1.5, I guess, 53, minus H2, which is 233. Okay, all of them are kilojoules per kilograms. Okay, all of them are specific. Then multiplied by the electric generator efficiency. So yeah, basically that will be your final answer. Okay, let me do it quickly in the calculator for you. Multiply by 1 minus 225, 2.65 minus 225.94 over 353, 1.53 minus 223. Okay, multiplied by 0.96. And yeah, there we have it. It is approximately, okay, 32%. Okay, so let's check it. Okay, let's check it from the answers. I guess the final answers are written in the question there. Okay, so it is 31.5. Of course, we didn't do approximation or much approximation. We multiplied everything together. Okay, and if you look at the solution, okay, the solution manual for this question, he did the approximation. Okay, for the pump work. Okay, Vp2 minus P1. Okay, so our answer is gonna be somehow a little bit different. Okay. Okay, but again, this is an acceptable range, only 0.5%. Yeah, what else we have? What is the second part of the question? He wants me to calculate the required rate of coal supply. Okay, now I don't need the the tables, okay, or the tables for that. What is the required flow rate of the coal? So remember, this is the combustion. Okay, let's say that the combustion happens in a furnace. Okay, and then heat. Okay, so heat here, we'll have some heat in. Okay, to the cycle. Okay, there. Yeah. So, and there is also an amount. Okay, so what amount of energy that will be produced here by heating? Not all of it is going to be transferred to the cycle, but only this is going to be 0.9. Okay, 85 of Q, okay, combusted. Okay, so let's me call it Q combusted. Okay, and this is gonna be, okay, which is equal to Q into the cycle. Yeah, so I know what is Q in to the cycle. Yes, I know what is Q in, okay, to the cycle. So what I can do, I can divide it by 0.85 to get Q combustion. Yes, and after I get Q combustion, then my m dot, okay, of coal will be equal to Q, okay, Q combustion over what? Over the heating value. Yes. Why? Because the heating value is kilojoules per kilograms. Okay. The heating value is kilojoules per kilograms. And the Q combusted is gonna be in kilowatts. Okay. In kilowatts, and then when I divide them together, then I'm gonna get kilojoules. Okay, let us do the Q combusted. We don't want to put it the capital one, we want to put the specific one. Okay, what if we did the specific one? It's gonna be per kilogram. No, we don't want the specific one, we want kilojoules here per kilograms. Okay, and if we multiplied it by m dot, we're gonna get kilowatts. Okay, so yeah, we need to put Q capital, okay, Q capital of combustion, okay, which the one is gonna be in kilowatts. Yeah. So now, what is our Q? Okay, it is H3 minus H2. Okay, so let's evaluate H3 minus H2. Okay, which was 3531.53. Okay, minus 233, which is 329.53. Okay, 329.53. So let me delete this. 329.53. 8.53. Okay, and then as I told you, divided by what? Divided by 0.85. Okay, to get the amount of Q combusted. And what is the heating value? The heating value is 2900 and 300. Okay, 29,000. Okay, and 300. So 29,000 and 300. Okay, and make sure that the units are consistent. So now we have this one is in kilojoule per kilogram. Okay, but per kilogram of what? Per kilogram of steam in the cycle. And this one is kilojoule per kilogram. Okay, kilogram of what? Kilogram of fuel. Okay, so this should be multiplied by the mass flow rate of what? By the mass flow rate of the steam in the cycle. Then after I multiply by the mass flow rate of the steam cycle, this will be in kilowatts or in kilojoules per seconds. And now my final answer for the fuel will be kilograms of fuel per seconds, which is the mass flow rate, okay, m dot of the coal or of my fuel. Okay, you know now how I get it. Okay, so just if you think about it just simply, this is the Q combusted. Okay, and now this one to make the Q as a total. Okay, a total heat addition. This is the same as the question that was asked for you in the quiz. Okay, some of you just calculated Qn. Okay, in the last question you need to calculate Q capital because you have enough inputs or enough givings to calculate Q capital N. Okay, you just multiply m dot by Qn, okay? Because you already have everything at point one in that question. So here in this question, what I have 175 megawatts. I have the power produced by the or the net electric power that was produced. Okay. So what should I do? 175, which is the net power produced, divided by H2, okay, or H3 minus H4 minus H2 minus H1. Yeah, so this is the compressor work, this is the turbine work to get the specific net power input, okay, network input, and then divided by this one is the power, okay, produced. So I will get m dot in this ratio. Remember, if I told you if you divide W capital dot by W small, you will get m dot always. Okay. So yeah, just do that or do this calculation, okay, and you will get the m dot of steam. Okay, just to save time, I'll show you it. I'll show it to you here. Okay, so yeah, this was the work.net. Okay. So I think he did in a different way, but again, you can do the same thing. So if you put w.net over H2 minus H1 or H3 minus H4, okay, H3 minus H4, and then H4 minus H1, you're gonna get this Qn. He did it in a shorter way. I didn't think of it, but again, it's gonna be the same. So because you have the overall efficiency, okay, of the cycle, now you can divide the w.net, okay, the w.net over the overall efficiency of the cycle to get the total Wn, yeah, because again, think of it in this way. This is the cycle, okay, and this is the generator, and this is the combustion or the furnace where the combustion happens. Okay, so we have, okay, these let me say like this is the N, okay, the actual N for the fuel. Okay, let me call this is the combustion here. It happens here, and here where the combustion losses happen. Okay, let me do it in this way. So I want to find this, okay, here, this one, this heat input. This one is the one that will tell me what's the ratio of, or what's the m dot of the coal. Because if I used m dot of the coal here after the losses are happening, then I'm going to end up with having a amount of coal that is less than what I supposed to do. Because you burn an amount of coal, let's say that I have 3 kilograms of coal. Okay, it's not going to be this small number, but let's say that I have 3 kilograms of coal. Okay? And I know that there are some losses that will happen. I need to burn this 3 kilograms of coal to account for the losses that will happen, but not to like say, okay, this is the amount of energy that I need. So now I'm going to burn 2.9 kilograms of coal or 2.5 kilograms of coal. Then these half will be lost. You need some of it to be lost here, okay, during the combustion process to have the net amount of coal or the heat net, let's say, that will enter to your cycle. Okay. So yeah, so because we have here what is the net output, okay, what is the output of the from the cycle, which is 175 kilowatts, okay, or yeah, kilowatts or megawatts, we have it. So this amount divided by the combined efficiency is going to give me directly this thing here, okay. So yeah, and then you're gonna divide Q combustion, okay, over the heating value, which is going to be giving you m dot of the coal. Okay, yeah, as simple as that. So yeah, this is one of your homework questions, I believe. Okay, so and it is very easy Rankine cycle. Okay, it's one that is ideal, not an actual one, but it have a small idea here where you are using thermodynamic devices, or you have a combined thermodynamic system. Okay, yeah. So where's the other question? Or the third question, or the, yeah, this one. This one is a Rankine reheat cycle, okay? This is the problem that will take a lot of time for you to solve, because it has 6 points, okay? And if you have one like this in the midterm, then you need to solve very fast, okay, to be able to finish everything, especially if he wants you to calculate the thermal efficiency, then you need all the points, then it's gonna take some time, okay? So you need to really practice on it to be able to solve it in just a matter of minutes. Okay. Yes. So what is there? Consider a steam power plant that operates on a reheat Rankine cycle that has a net power output. So this is the net power output of the cycle. The work dot net, it is 80 megawatts. Steam enters the high pressure turbine, okay, the first turbine, which is point 3, okay. These are the states for point 3, and the low pressure turbine, okay, which are the states of point 5. Yes, because remember, this is the high pressure turbine, and now this is the low pressure turbine, okay, and this is let's say like this is the pump, okay, give me for this drawing, okay, this is the pump, and now this is the outlet of the pump, and the outlet of the pump will enter a boiler, the boiler, okay, and then we'll enter here the high pressure turbine. You need to memorize these, and then from the high pressure turbine it will go here to do a reheating process, okay. So here we'll have a reheating process, okay, and then again from the reheating process it's going to enter the low pressure turbine again, okay, low pressure turbine, and then from the low pressure turbine to the condenser, okay, here to this point, okay, outlet of the low pressure turbine is going to enter a condenser, where it's going to reject heat and then go back to point 1. So this is point 1, point 2, point 3, point 4, okay, sorry, no, point 3, point 3 is here, point 3, point 4, point 5, point 6, okay. So this is the states of point 5, and then leaves the condenser as a saturated liquid. Remember, if he didn't give you this information, you need to assume it, which is saturated liquid at the inlet of the pump. So it leaves the condenser as saturated liquid at a pressure of, so these are the properties of point 1. The isentropic efficiency of the turbine is 80%. This is the isentropic efficiency of the turbine. This is the isentropic efficiency of the pump. Show the cycle on the TS diagram with respect to the saturation lines, okay, and the dotted lines, of course, the actual ones, and the actual and the real ones, okay. Oh, sorry, the isentropic ones. And also what he wants, the first thing, the quality or the temperature, if superheated, of the steam at the turbine exit, okay. So here in the turbine exits, here we have a turbine exit, and here we have a turbine exit. So both of these can hit the dome, okay. So let's say we are starting from here, we are going from here then to there, as we have in the boiling process, okay. So this is point 3. Now, point 4 can go down and enter here, okay? It's not necessarily that you'll find that point 4 is here in the saturated region. Point 4 can go all the way down and enter here, okay? Enter the dome. It can enter the dome. It will not go too far. And then you have point 5, okay, which is again gonna be superheated. And then point 6 also can either enter the dome, okay, or be outside, or be, of course, on the line. Okay, so you need to know, okay, if this point, the first turbine outlet, okay, is it superheated or is it a mixture? Okay, so if it's superheated, find for me the temperature. If it's a mixture, then find for me the X. And here also, is it superheated or it's a mixture? So if it's a mixture, find for me X. If it's superheated, find for me the temperature. Okay, so this is what he is asking for. And then the thermal efficiency of the cycle, and then the mass flow rate of the steam, which is again, you know, always the rule for this. It's going to be W dot over W small. Okay, net. Okay, as we did before in the last question. So yeah, let's again do it the same way. I need the H's at all the points, okay, because I need to calculate the thermal efficiency. So H1, H2, H3, H4, H5 equal, equal, and H6. And after that, I can solve the question. Okay, so let's go to our code. What the first thing we have? Let's calculate first for 1. So for 1, I want the H, given that I have the what I had the pressure, yes, and yeah, so I need HL, okay, from the pressure. So what was the pressure at point 1? I forgot it. Let us go to it. The pressure at point 1 was, let me enlarge it here and move it to the center, or move it slightly bit here so I can see it. The pressure at point 1 is 10 kilopascals. Okay, so 10 kilopascals is gonna be 0.1 bars. Okay, always make it in bars. So what is the H? The H is 191.81. So the first H here is 191.81. Put the pen, 191.81 kilojoules per kilograms. And then what is H2? Remember, you always calculate the actual cases. So I will not care by H2S. I want to know the H2A. Okay, so at first calculate the H2S. Okay, H2S is gonna be when you calculate the H, okay, from the pressure and the entropy of point 1. Okay, so you make entropy constant. Okay, so let's find at first the entropy of point 1. Yes, this is the entropy of point 1. Okay, or let me do it in the way that you are going to do it in the exams. Okay, so because in the exams you don't have tables A7. Okay, so let me find at first the specific volume. Okay, the specific volume of point 1. Yes. Now this is the specific volume of point 1, which is 0.00101. Okay, 0.00101. Yes. So this is the specific volume of point 1, 0.001. Okay, let me write a couple of digits, 10103. Is that correct? So let me just take it again. 00101. Oh no, 00. Okay, I put 2 zeros. Okay, and then 101. Okay, and then 03. 101 and then 03. Okay. So this is, of course, in meter cubed per kilograms. Okay, and then how can I get H2S, the isentropic one? The H2S is equal to the volume, okay, at 1, pressure 2 minus pressure 1, okay, plus the H1. Okay, because the work is H2 minus H1, and this is the work. So you put H to the other side, so it's going to be positive. So yeah, just multiply 0.00101003, the pressure difference, which is, again, here we have 10 megapascals. This is the higher pressure, okay? Use the pressure of the high pressure turbine, not the low pressure. The low pressure turbine is not the same as this pressure. So here in this cycle, you have three pressure limits: the upper pressure limit, the intermediate pressure limit, and the lower pressure limit. So here I have, as we said, 10, okay, megapascals, which is 10 times 10 to the power 3 kilo pascals, and this one is 10 megapascals. Okay, so 10 megapascals and 10 kilopascals. Okay, 10 mega and 10 kilo. This is not multiplied by anything. So yeah, what is H2S? Okay, 0 0.00, 0 0.001 or 103 multiplied by 10 times 10 to the power 3 minus 10, okay, plus the H1, which we calculated. So it is 201.9. Okay, and now I go to the efficiency. I go to the efficiency of the pump, okay, which is 95%, and then this 95% is gonna be equal to H2 actual minus H1 over H2. Sorry, this here is the actual, here's isentropic minus H1. So what is this number? Okay, do just an equation in the calculator where you put 95%, okay, equal to this value. I know it. Okay, I know it, which is the actual or the isentropic one, which was 201.9. Yes, minus what is H1? 191.81. Okay, over x, which is the unknown for me, minus again 191.81. So yeah, there you go. Just let me wait for the calculator to give me the value. So it is 202.43. Okay, kilojoules per kilo. Oh, 1 minute. This is a power producing device. So okay, don't make this mistake. This one is H2. The actual, because the isentropic in this case gives more work because there's a power producing device. So I need to flip it. Okay, 1 minute for that. 201.9 and then x. So the solution will be, yeah, just 201. Okay, that's how you spot your mistakes. You always should have an H2A, and a value for H2A that is greater. Okay, oh, sorry, yeah, that is less than the H2S, and you should always have a value of H for the turbines, which is H4A or H6A, that is higher than the HS. Okay, because those are power producing devices, and this is 1 minute. We are here in the compressor. Okay, don't worry, you have the equation already there. Let me figure this with myself. Okay, you can use the equation directly, you don't need to understand it. But this is H1. This is a compressor. Compressor should, if it's isentropic, should draw less work. Okay, so what's the lesser ratio? Yeah. Just like this. This is a compressor. Okay, that's the benefit of having some of you here with me in the tutorial. That's no problems. Yes, so the first number was the one that's correct. Okay, 95% equal to HS, which is 201.9 minus the 191.81 over the X minus 191.81. Okay, this is a compressor, which is gonna draw less work when it is isentropic. Draw less work when it is isentropic. So the isentropic values should be up. Okay, kilojoules per kilograms. This is the actual one. Or we could have done it in a simpler manner, okay, which we are going to make the entropy constant, but this method you cannot use it. Maybe don't you have the tables? So you find what is the entropy, okay, of 0.1. And yeah, this is the entropy of 0.1. And then you tell him, give me the H when I know the pressure and the entropy. And you tell him that your higher pressure is 10, okay, 10 megapascals, so it is 100 bars, okay, and then comma, and then the previous answer, and then hit enter, which is 201.87. Okay, so this is the small deviation amount that we got here. It is 202.43 is from the error involving using this method. Okay, yeah, so what else we have? Yeah, let's go to point 3. So point 3, I have everything at it, which is the inlet of the turbine. Okay, we have the inlet on the second turbine. So I need H, given that I have a pressure and the temperature. What was the pressure? It's 100. What was the temperature at the inlet of the first turbine? The temperature at the inlet of the first turbine is obviously 500. Yes, the high pressure turbine. So 500 Celsius here and 10 megapascals, which is 100 bars. This is the H3, which is 3375.06. Okay, 3375.06, 3375.06, yeah, 3375.06 kilojoules per kilograms. Okay, what is H4 actual again? Okay, and what is H5 actual? H5 is not H6 actual. Okay, all of these you should do. So what was the isentropic efficiency? The isentropic efficiency of the turbine is 80%. Okay, so for both turbines. Okay, he says that it is 8%, so it is going to be for both turbines, not for one of them. Okay, so what is the isentropic efficiency of the, or how can we get H4A? Okay, now for this one, you cannot do that approximation, which is volume, okay, because this approximation only stands for liquids, okay, because the liquid is incompressible, and then the V is gonna be the same. But the steam, no, the amount of changing in the specific volume of the steam is gonna be very high. So you cannot make this approximation of keeping the V constant. So what can we do? We should do the entropy, okay, the S thing, and go to table A6. So let's take the S of 0.3, okay, and make it constant at first. So this is S of 0.3. I want S. Now I have, this is the value, this is the S at 0.3. And what is, tell him, what is the H given the pressure and the entropy, okay? And what is the intermediate pressure there? Okay, when I go down to 0.4, what is the intermediate pressure? You remember I've told you that you work on 3 pressures here. So what is the intermediate pressure? He told me the intermediate pressure. Yeah, it enters the low pressure turbine at 1 megapascals and 500 Celsius. Okay, so this is the intermediate pressure. Okay, here let me draw the point, these points on the TS diagram for you. Okay, so this is 0.3. 0.3 is gonna be going there down, okay, till 4. Okay, and of course it's not gonna hit this if we went isentropically. Okay, so I will not go, of course, isentropical. I have some deviation here, so I'll go here to this 4S, this is 4A, the one that I want to find. Okay, 4A. And then after I find 4A, he tells me that this is the inlet for the that turbine, which is this is 0.3, this is 0.5. Okay, and he tells me that this pressure here that you see here is 1 megapascal. Okay, this pressure is 1 megapascal because again it's going to operate on constant pressure. Okay, but the temperature here is 500. The temperature, of course, is not going to be constant. Okay, but this process takes place in constant pressure. So I need to know the properties of this point. Remember that the first question tells us if this is a mixture, then give me its X. But if it's not a mixture, then give me its temperature. We're going to check if this is a mixture or no. Okay, now. So yeah, what is the H? Okay, giving the pressure, the intermediate pressure, which is 1 megapascals, which is going to be 10. Yeah, because you multiply by 10. Okay, and we have the entropy, okay, which is the I and A and S. Okay, so yeah, he gave me, this is the H. Okay, this is the H for that. Of course, you cannot do this directly. Okay, this is just because we are using this sufficient code here, or efficient code, but let me tell you what you are gonna do basically. Okay, follow it with me in the tables. So you go to tables, okay, and you know that you have that entropy, which is 6.99, okay? So you see that's the value of the entropy. And what's the value of the pressure? It is 1 megapascal. So you go to table A4, okay, or no, let me say A5, because this is the one that have the pressures. And 1 megapascals is equivalent to 1000 kilopascals. So I go to the 1000 kilopascals, and I see this value of entropy, which is 6.599. Let me call it 6.6. So for 6.6, it's much higher than SG. It's not much higher, but it's higher than SG. So this is clearly superheated. Then I go to table A6, and I go to that pressure, which is 1 megapascals. Okay, and I go to seek for that entropy, which is 6.6, as we said. So yeah, it is between 6.58 and 6.69. Okay, so it's gonna be at a temperature somehow 185, 180 something. Okay, so let's see what's the temperature here. Okay, let's tell him that X. So give me the temperature. Okay, if I gave you H, okay, H, and the pressure, if I give you because the pressure comes first, and H. So the pressure is the same, and let's give him this H, which is the answer, the one that we found before. And yeah, as I told you, it's gonna be somewhere around 185. Okay, so this is the temperature. So this is the solution, the first part of the solution for part A. This is superheated, not a mixture, clearly, and it have this temperature. Okay, so yeah, this is but again, remember, all what we are doing now is for the isentropic case. So yeah, we didn't solve part A yet, sorry. Let's now find what is H for the actual case, because this is H isentropic. So how can we do that? You see how the cycle is very long. So the isentropic efficiency of the turbine, which is 80%. So the 80% is gonna be equal to, okay, and this is a power producing, not consuming like the pump. So you can use the equation directly, okay, but I prefer to do it like that to not memorize it. So here we have H4, and here we have H4, and here we have H3, and here we have H3. Okay, but now here's the trick. Okay, so where to put isentropic and where to put actual. Okay, because this is a power producing, you want to produce work. So the isentropic work is gonna be more than the actual work because you are producing, not consuming. So here the isentropic, and here the actual. Yeah, just like that. So now we calculated the isentropic. I need H actual. So what is H actual? 80%. 80% equal to, I know what is my H3, which is 3375.06, 3375.06 minus the X that I want to find, okay, which is the actual. And then down there, I put the isentropic. And what is the isentropic? I found it here, okay, this is the isentropic one. The H isentropic, which is 2783.64, then shift solve, and then you get your actual. Yeah, so this is our actual. It is 2901.92. Okay, this is our actual. Or you can do another thing, which is that find the work out for the compressor and then multiply it by the efficiency. And then what you do, you subtract it from H3. This is gonna be somehow tedious. Okay, it's not tedious, but just longer. This is gonna be H3 minus H4S. Okay, so okay, this one is the isentropic. Okay, which is here. Where did we wrote the equation? This one is isentropic. Yeah, so you multiply by the 80%. Okay, but don't do it. This one is easier. So now we got this one, and then again. Okay, and as I told you, you tell him what temperature there and what we have. So let me go back to the code. Okay, and then tell him, give me, or let's do it in table A5. Okay, go to A5 and then see what value of pressure there you have, which is, as we said, it is 10 megapascals, which is 1000. Okay, and we need to see this new H. Okay, where is this new H lying? So this new H is much higher than UG. Okay, oh sorry, HG, which is 277.1, and we got 2900. So yeah, it is superheated. And let's get its temperature. So I want the temperature from the pressure and the H. Okay, and where is the new H? The new H, I'm gonna write it, okay, because we calculated manually. It is 29, what is it again here? 2901.92. So 2901.92. So hit enter. The temperature is 231. Okay, let me go to table A6 just to double check it. So 231, okay, at 1 megapascals. 231, so it is between 200 and 250. So yeah, in that range, I have the 2900 enthalpy there. Okay, and now let's calculate H5 directly because we have the properties at 5, which are the temperature and the pressure. Here I have the pressure, here I have the temperature. Okay, temperature and pressure. So 1 megapascal and 500. So I can report H5 directly. Go to the code. Now what do you want? You want H, given pressure and temperature, pressure of 10, temperature of 500. Okay, and now this is the H. Okay, remember that this is lower, or no, it's higher than the H that you got before. Okay, this is 3.4, yeah, and this is 6.5. Okay, so where was it? 3.375, yeah, because this one with higher pressure than this one with lower pressure. Okay, but they are at the same temperature. So if we did it in the TS diagram, it's going to be something like this. Okay, so this one in the pressure of 10 megapascals, and here we go. Okay, of course we're gonna go in not a straight line. Okay, so this 0.4, the actual one, and this is 0.5. Okay, here, and this one is 1 megapascal. So if you go to read the value of H here, okay, or the S here, so the S here is clearly greater than the S here, so the H of course is gonna be greater than the H here. Okay, this is just for you to double check it, but again, it will not like benefit you much in the solution. So what is the H? 347.9. Okay, let's me point it 0.0037. I forgot the value. 347.9. Okay, kilojoules per kilograms. Again, I should do the same thing from 0.5 to 0.6 because I have 6 actual. And what is 6 actual? Okay, so I have the pressure here, okay, which is the pressure of the condenser, which is 10 kilopascals. And I have the H here, so I need to get the S, okay? So what is the S? Again, give me the S when I have the pressure and the temperature. So there you go, this is the S. And when you check it in the exams, so you say like, yeah, I have 7.763. So how can I check where is this point exactly? So you go to the table, A5, and then you say, okay, I have 10 kilopascals, okay, for the lower pressure. And then when I have 10 kilopascals, okay, I need to go and check this value of entropy. So this is between, okay, so when it is between, meaning that this point is probably going to be a mixture. Okay, of course this is not the actual point, this is the isentropic point. Okay, but again, yeah, it's going to be somehow close to it. Okay, so this is the isentropic point. Okay, and now let me get what is the H there when I have this answer, and when I have the pressure, which is 0.1. Okay, and give me the H when I have the pressure and the temperature, the pressure and the entropy. There you have it. He gave you the H when you have the pressure and the entropy, which is 2461. Okay, so this value, of course, you're gonna get it from the table, but as I told you, we're using here the code to save some time. So this is H6S. Okay, how much it was? 2461.11. So 2461.11 kilojoules per kilograms. What we're gonna do, we're gonna apply the equation again, same equation here, but just change the points. So here 5, 5, 6, 6. Yes, 80% equal to, what is H5? Let's go to it. It's 3479 minus minus. Up there I have the actual, which is my X I want to find. And here we have our S, which is 2461.11, and then shift solve that to get your new H. Okay, so this one is 2664.688. Okay, so it is kilojoules per kilograms. Okay, this is our H6A. So yeah, he wants me to see if this one is or if this one is is it outside the dome or inside the dome. So I can give him either the X or the temperature. So what is what is the state there? It will have the same pressure. Of course, the isentropic point and the actual point both have the same pressure, but they are different in the entropy and in the H. So go to 10. I need to see H. Yeah, clearly H is higher. No, it's between HG and HF. So it is between, because HG here, as I can see, it's 2580. So what I got here, no, actually no, it is not between. It is outside. Okay, so yeah, it is outside. The isentropic point was in between, but this one is outside. Yeah. So what is the temperature here? Let's go to table, as we said before. Let's go to table A6 because this is superheated, and then try to get the temperature there with the 2664. So, and what was the pressure? It was 10 kilopascals. 10 kilopascals. I'm going to the tables, and I see that 10 kilopascals is 0.01 megapascals, right? Okay. So when I see for the H there, which is 262, okay, it is between 50 degrees and 100 degrees. So it's between 50 degrees and 100 degrees. 50 and 100. So let's check it using the code. Okay. Okay, of course you are gonna do interpolation again. So yeah, what I have the pressure and the enthalpy. Please give me the temperature. So I tell you that the pressure is 0.1, and I give him not this enthalpy, give him the actual enthalpy. So what is it? 2664. Yeah, 2664.688. Okay, 2664.688. So 2664.88. I always forgot what this is the number. No, 2664.688. Yeah, my bad. 6, 8, like this. So hit enter, and as I've told you, it is between 100 and 50 degrees Celsius. So this is the temperature. This is part 1 or part A of the problem. Okay, where was it? Okay, don't tell me that I was solving all the way using this. Yeah, okay, this is the question. Yeah. Remember? I was afraid that it was that question I'm solving. Okay, 88.1. And what we've got in the code, so it is 88.06. Okay, so that's fairly close. And now what should we do? Okay, yeah, we now need to calculate the thermal efficiency and the flow rate of the steam. The thermal efficiency is easy. Now you have all the H's, and remember, always use the actual H's. So I'm gonna say, like, let's use 1 minus, let us not use this one, we use it a lot. Let us use the thermal efficiency is work, okay, net over Qn. And this is equal Qn because we have 2 Qn's, and we have for the work net, okay, what you should do. You have 2 turbines and 1 compressor. So say H5 minus H6 actual. Always use actuals. Plus H3 minus H4 actual minus H2 actual minus H1. So all of these is the work net. 2 works output, 1 work input. And for the heat addition, I have 2 heat additions. So I have H3 minus H2 actual, again, minus H5 minus H4 actual. Okay, sorry, plus, because there are 2 heat additions. Or if you used 1 minus Qn, Q out minus Qn, you have only 1 Q out, which is H6 actual minus H1, and you have 2 Qns, which are those. Okay, always this equation is easier, but sometimes, like, maybe you just want to use this one. I don't know. Yeah, so let's put everything. I've memorized it, so let us apply it directly. I will do it directly in my calculator just to make sure that the answer is correct. So 3479 minus, and what was H6? H6 is 2664.688. and then plus. Okay, so always put the brackets, don't forget them, and then plus the second one. Okay, the second work, which is H33375.06 minus the what is it, for 2901.92, and then the last step is minus, of course, the pump work, 202.43. Sometimes you can eliminate the pump work because it is very small. Okay, if you can see here, it's very small compared to those works, but don't do it always. Okay, 202.43 minus 191.81. Yeah, I can do now with eliminating the pump work and show you what will be the value of the error. Okay, this will be a good practice. And then H5, which is 3479 minus, now I should do 4, yeah? So 2901.92, and H3 minus H2, so 3375.06 minus 202.43. So then put equal, I'm getting an efficiency of in the answer of where did we write the equation? Yeah, here I've got an answer of 34%, 0.05. Okay, 0.05 to be more accurate, and it is, yeah, somehow close. They approximated the half to be 0.1. Okay, so what happens if we eliminate the pump work, as I told you? So we don't subtract it up there. We'll get an efficiency of 34.33%. Okay, so maybe this is going to be a trick for you. If you don't have time and you see that the compressor work is very low, just eliminate it and then tell the professor that okay, the error is going to be low anyhow. Okay, but don't do it always. Do it if you don't have time, as I told you. And yeah, so that's it. And this one is very easy. I'm not going to do it. Okay, but remember, always when you want to calculate the mass flow rate, it's going to be the work capital dot net over the work small. Always a small value of a capital value. A capital value of a small value is going to be giving you m dot. Okay. So yeah, how can we calculate this one? You know, it is the work net, which is H5, okay, minus H6 actual, and then plus H3 minus H4 actual, and then minus H2A minus H1, okay, and you remember, and this one is given for you in the question. So yeah, that's it. Okay. Yeah, so if you don't, no, there is no one. So yeah, thank you everyone, and yeah, see you next time. Okay, in the maybe in the session or the interview session. Assalamu alaikum.